Swayam Prabha. Digital India. Educated India.
Welcome to Structural Dynamics class. So in this class we will study classical and non-classical damping. So what is actually damping? So let me show you an example. Say assume that this is a pendulum and I am giving say initial displacement and it is oscillating. So after few cycles it is coming to rest. So how it is coming to rest? So it is coming to rest because the frequency, that the vibration energy is dissipated. So where it is dissipated? It is dissipated in two forms. One is friction between this point, this edge and my finger, that's friction. In the form of heat it is getting dissipated, and then second one is air resistance. So in these two forms the entire energy what I am supplying for oscillation is getting dissipated. So this is damping. So in a way damping removes the vibrating energy and in each cycle it removes. Now let us discuss what is classical and non-classical damping. The damping matrix. So if we are talking about multi-degree of freedom systems, we need to define damping matrix. So in single degree of freedom system we define damping as a term. So generally damping is a non-linear phenomenon. So because it depends on the displacement and velocity time history. So if more velocity, damping is proportional to that. So in earlier cases what we have done was we have made damping term as constant in linear elastic analysis. Now when it comes to non-linear analysis it is not anymore linear. So damping term also is non-linear. It depends on the history, that is u and u dot, that is displacement time history and velocity time history. Now this damping matrix, how do we define? Damping matrix must be defined completely if classical modal analysis is not applicable. So that means what? We cannot fix this damping value, so damping value varies. Now classical modal analysis is not applicable to non-linear analysis even if damping is in classical form. So in these two cases, when non-classical damping is there, so there we have to define damping matrix, and when it is non-linear analysis, even if damping is classical, we have to define that. So how do we define? So Rayleigh has given a way to define this damping matrix. So consider first mass proportional damping and also stiffness proportional damping. So if you take this structure, this in this picture you can see this one. So when structure is oscillating or structure is vibrating, so damping present in the degree of freedom or in that floor is proportional to the motion of that floor. So we can call that as damping is proportional to mass. So and the second one is damping is also related to the interparticle friction, so that gets emitted in the form of heat. So it is also proportional to stiffness. So then combined form we can write, so damping is equal to alpha, because if we have to remove the proportionality we have to introduce some constant. So damping is equal to alpha times mass matrix plus beta times K matrix, that is stiffness matrix. So now we need to find out what are these alpha and beta values. So alpha and beta are constants. So as we can see, if you match the units, so this alpha units must be per second and beta units must be in the form of second, so that it matches with the damping. So C matrix can be made diagonal by virtue of its modal orthogonality. If we use modal orthogonality principle and apply that principle, so we can make that as diagonal matrix. So C matrix can be made as diagonal matrix. So now if the stiffness proportional damping appeals to intuition. Why? Because it can be interpreted to model the energy dissipation arising from the story deformations. And in contrast, mass proportional damping is difficult to justify physically, because as I told you, it is related to air friction. Okay, so it's mostly negligible. So Now when we have say modal matrix or modal vector, so if we apply say modal matrix as phi transpose and multiply by phi on both sides of the equation, we will get the diagonal matrix because we decouple the equations and solve simultaneous equations. So C is equal to alpha times m plus beta times k. So we are pre-multiplying and post-multiplying with phi transpose and phi respectively, all these three terms. So if we do that, what we get is alpha times phi transpose m phi is a diagonal matrix, that is 1 1 1. So these are masses. And then if we take this 2 omega 1 zeta 1 0 0, and in second row 2 omega 2 zeta 2, third term 2 omega 3 zeta 3. So this is coming from something like this. So mass matrix has m 0 0 0 m 0 0 0 m. Now if you take m as common outside, so in this one in C 0 0 0 C 0 0 0 C, something like this. So m by C term, so if I divide entire all these terms by m, so C by m is 2 omega 1 zeta 1, 2 omega 2 zeta 2, 2 omega 3 zeta 3. So that is a also. So how this has come, please refer to single degree of freedom systems lecture. And here mass by mass will be 1 1 1 diagonal term, and k by m will become say omega 1 square, omega 2 square, omega 3 square, corresponding natural frequencies of mode shapes. So now the thing is how to get this alpha value and beta value. Now let's look at the equation. So if we expand this equation, earlier equation, so what we get is 2 zeta omega 1 is equal to alpha plus beta omega 1 square. So the same thing I am writing, 2 zeta I omega I is equal to alpha plus beta omega I square. So this is corresponding to that mode shape or that idealized single degree of freedom system. So in modal analysis, when we have mass matrix, when I have K matrix, and when we have C matrix, so in modal analysis what we do is n degree of freedom system, say if it is 3 degree of freedom system, we are converting that into 3 single degree of freedom systems, something like this. So this I is corresponding to this, so omega I, so omega 1, omega 2, omega 3, like that. So now from this we can get zeta I is equal to alpha I by 2 omega I plus beta into omega I by 2. So zeta I is say 1 by half alpha by omega I plus beta into omega I. So this is a zeta equation, so damping equation. So what is the damping present in say each mode, we can calculate from this one. So for that, so what we do is zeta I, zeta j. So if I replace j with I, so if I with j, so what I get is corresponding values. So I get alpha and beta as matrix. So in this one, so what I need to do is like I estimate the damping values and then find out alpha and beta by doing inverse of this one. So that's how we find alpha and beta values. So once alpha and beta values are there, we can find the damping in any mode shape. So C is equal to beta times K. So that means what, zeta is beta omega by 2. So stiffness proportional damping effect, so it is linear. And then when it comes to mass proportional damping effect, so C is equal to alpha times m. So in that case zeta is equal to alpha by 2 omega. So it is mass proportional damping effect. So in case of Raleigh's damping, both are combined. So that means what, so what we are getting is, you can see this mass and stiffness proportional damping. So in the horizontal axis you can see omega. So now what we have is, as the natural frequency of the structure or say a mode shape is different, so in first mode shape it can be here, so this damping value we use, second mode shape we use this damping value, third mode shape mode we will use like this, different this. Okay, this is one thing. And then there is another use of this one. So another use of this means, say if I've taken say a tall building, So I found out, say, omega of the tall building is equal to, say, under root k by m in this form. Now because of the vibration, so or say earthquake effect, so continuously, say, this natural frequency of the structure is reducing, or natural period is elongating. So now what happens is the natural frequency is reducing and natural period is increasing. So damage increases natural period. So that means what? It reduces frequency. So what happens is, in first case, if my damping is here, then if this frequency is reducing, so then I am getting reduced damping in some cases. And in some other cases, say if my natural frequency is here and because of damage it is reducing, so then my damping increases. So that means what? Where we are in this curve, we need to be very careful in applying damping. So because zeta has an effect of reducing vibration amplitudes. So these vibration amplitudes, say maximum amplitude, if we are calculating in a wrong manner, so then that leads to either over evaluation of the structure's response or under evaluation of the structure's response. In this class we have studied so how to calculate, say, non-classical damping matrix. So the two forms are mass proportional damping as well as stiffness proportional damping. So we have developed an equation in this class, that is C is equal to alpha times m plus beta times k. So by using different mode shapes, we have evaluated this alpha value and beta value, and then we have developed or drawn the curve like how the damping values change with the natural frequency or natural period of the structure.